Imagine you're climbing a mountain and you want to know which direction should you travel to, for instance, get up the mountain as fast as possible, or alternatively, which direction should you travel so that you stay at exactly the same elevation, that you sort of contour around the mountain without going up or down. In this video, we're going to tackle that problem mathematically, and then we're going to see that it's intimately connected to the idea of the gradient vector, a vector that's appeared previously in our multivariable calculus course. Now, I have a sort of sample mountain here, looks a little bit like a saddle point, and the first thing I want to do is to put a bunch of contours on it. So a contour curve is just specifying some height and then drawing a curve on that mountain, which are all the points of that exact height. So for example, I might have a height where it's got a z component of 2 or 1.6 or 1.2, and it goes down and down from there. But either way, these contours, or as they're sometimes called level curves, are just constant heights of the function. Now this is the three-dimensional picture, but there's also a corresponding two-dimensional picture. If I just take all those level curves and isolate them down in the xy plane, you get a picture in the xy plane. I've drawn this with perspective, but maybe I'll just sort of rotate it to the standard way it's presented. You have your normal xy plane and your list of contours, which are really the projection of the contours down onto the xy plane. Now, the reason the contour plot is useful is that if you identify what the z is for each of these contours, so the 2, the 1.6, the 1.2, and so forth, then the way you can visualize this is saying over top of the contour associated with z equal to 2, then the function has a height of 2, and that is going to be true at any point on that particular contour or that particular level curve. So thinking about this as a mountain, if you stand on some spot on the mountain, you're standing on some contour, the contour with that particular height. And if you want to not change your height at all, you just walk along that contour. And if you're actually on a mountain, I mean, this is visually obvious. It's just I want to walk in some direction so that I'm not stepping up or stepping down. I'm just going horizontally. But then the other question is a little bit less obvious. Which direction should I go to maximize the change in my height if I want to climb the mountain, for instance, as fast as possible? So we want to try to solve that mathematically. Okay, so let's abstract this idea a little bit. Let me imagine that I've got some curve, some r of t. It's got an x component, it's got a y component. So it lives in the plane. And what I'm saying is that along this curve, I have some function f, and that the function has a constant height anywhere along that curve, that the f of the x of t, y of t is just constant. Okay, well, let's try to do a bit of calculus on that fact. Why don't I take, for instance, the derivative with respect to t of both sides of this? Well, on the right-hand side, the derivative of a constant is 0. That's going to be easy. But on the left-hand side, this is a composition. This is the derivative of f of x and y, where x and y are themselves each a function of t. So I'm saying I want to take the derivative of a multivariable composition. We've seen how to take the derivative of a multivariable composition in a previous video, namely, it's the chain rule. And so if you plug in chain rule, what you get is the partial of f with respect to the first variable x, and then dx dt, plus the partial of f with respect to the second variable y, and then multiplied by dy dt. And then this has to add up to 0. The derivative of a constant is 0. We've seen this type of computation before, and indeed we can actually clean it up a little bit. This is the sum of two things multiplied, and so I'm going to try to interpret this as a dot product of two vectors. The first vector is the partial of f with respect to x and the partial of f with respect to y in these two components. And then the second vector is the derivative of x with respect to t and derivative of y with respect to t in its first two components. And then this is exactly the same thing because how is dot product defined? You multiply the first components and then you add the multiplication of the second component. So indeed, these are exactly the same statements. The reason why I like it written this way in terms of vectors is I can give special names to these two vectors that I have. The one on the left, the partial of f with respect to x and the partial of f with respect to y, that vector, is called the gradient of f. That is our definition of the gradient of f. And then the derivative of x and the derivative of y with respect to t, this is just, well, it's the derivative of r with respect to t. This is the tangent vector we've also seen previously. So nevertheless, what I get is this expression that the gradient of f dotted with the tangent vector dr dt is equal to 0. Okay, so let's just focus on that bottom equation, the gradient of f dot the tangent vector equals 0. Now I have a great interpretation of what the gradient of f is. I already knew what the tangent vector was, the dr dt. We've studied that previously. So if you have some level curve, the dr dt is just tangent to that curve. And then because the gradient of f has a dot product of 0, which means it's normal, then what is the gradient of f? It is normal to the curve at that point. Okay, so if we return to our diagram here, notice that I have a red dot in my contour plot, so I'm going to pretend that I'm standing on that red dot. Well, then I can tell you what these two different vectors are. The dr dt, the tangent vector, goes along the curve. And if you travel in the direction of the tangent vector, you do not change your height. You're going along that level curve, so your height function is constant. And then the normal vector is going to be orthogonal to the tangent vector. It's pointing away from the level curve. And this sort of makes sense because the level curves are going to have different heights, and so as you go from one level curve to the other curve, your height is changing. So it leads me to think that the gradient definitely has something to do with increasing my height function. But let's dive in a little bit more deeply. And before we can do that, I actually want to remind you of something from a previous video, the idea of a directional derivative. So in this graphic, a lot of things are going on. The first thing I want to pay attention is the arrow in the base, this purple arrow. This is in the domain. And what it is doing is telling you the direction in which I want to compute a directional derivative. And then when you've decided a direction, the blue curve is slicing through the surface in that particular direction. If you have a direction and you sort of imagine slicing it, the blue curve would give you that slice. And then the red line is telling you the slope of that curve. In other words, the slope of that red line is the directional derivative in whatever direction you're looking. So this was our pictures of directional derivatives, and indeed we'd seen in our previous video that the so-called directional derivative in the u direction of our function f was given by the gradient dotted with the u. Well, that should seem similar. Gradient dotted with u, I mean, that's exactly what we were just talking about before. It was a gradient dotted with the tangent vector. So we can sort of see that there's a relationship between here, but we want to be a little bit more clear about what that is. So let's just focus just on the equation. And what I want to do is take the dot product and replace that with the length of the gradient, the length of this direction vector u times cosine of theta. This is just from our definition of the dot product. And I'll note here that this formula looks awfully similar to the other formula that we've just been playing around with. It's a gradient dotted with something else. It's just that now with the directional derivative, I have a generic u versus the specific dr dt. Okay, so looking at this gradient of f, gradient of u, cosine theta, depending on the value of theta, sometimes this is large, sometimes this value is small. It depends on that angle theta between the two different vectors, the gradient of f and the u vector. Well, in the case where theta was pi over 2, cosine of pi over 2 is 0. So the smallest magnitude of the directional derivative, i.e. when the slope is smallest in magnitude, happens when theta is equal to pi over 2. And if theta is pi over 2, what this means is that the gradient and the u vector have a 90-degree angle between them. Well, that's the same thing as saying their dot product is 0. So in other words, the smallest magnitude of the directional derivative occurs when you have a dr dt as your direction. So if you're traveling in the direction dr dt, you're traveling along that level curve, you're going tangent to that level curve, then, as you'd expect, the directional derivative is just 0. Because if you're going along a level curve, you're not changing your function at all. Your slope is just 0 as you go along a level curve. And so everything just makes sense here. Our directional derivative traveling in the tangential direction is 0 as we'd expect. Okay, what about the largest magnitude? Well, cosine, the maximum value of that is 1, and one of the cases that happens is when theta is equal to 0. So I can say that the largest magnitude is going to happen when theta is equal to 0. Of course, if theta was equal to pi, you get the same value, but the negative of it instead. So if I don't care about plus or minus, then I'll just use theta equal to 0. Okay, so in this scenario, I have my gradient vector, I have my u vector, and I'm saying that there is in fact an angle of nothing in between them. This is just saying that the u vector is parallel to the gradient vector. And so now we have our interpretation of the gradient vector. Gradient of f is the direction you travel. It's placing the role of the u. It's the direction you travel when you want to increase your slope as much as possible. When you want to have the largest directional derivative. So the way I like to think about this is that you can have your directional derivatives pointing in any different directions, but there's two that are special. When you go tangent to the curve, that is going to be your minimal slope. And when you go normal to the curve, that's going to be your maximal slope. All right, so let's return to our contour plot. Let's put our point on it once again and try to put these two different vectors. So first we have the tangent vector, the dr dt, and indeed this goes along that level curve. And so we're going to have no increase in slope, aka its directional derivative is 0. And then we're going to have our normal vector, and our normal vector is going to point orthogonal to the curve or normal to the curve. And it sort of makes sense because when you go in that direction of the gradient of f, it's pointing towards another level curve. You're at one level curve, it points to a second, to a third, and so forth. It makes sense that the normal vector would be consistent with the idea of that's the direction you go when you want to increase your height as fast as possible. It's the maximal directional derivative. Okay, so the next thing I want to do is try to interpret this in a little bit more of a real-world context. This is a topographical map. It shows the mountain called the Golden Hind. The Golden Hind, by the way, is the tallest mountain in the mountainous island chain of Vancouver Island, which is where I live. I really love this particular mountain. It looks a little bit like this in the winter. It's kind of a big and imposing mountain. I do want to note that the mountain itself has this really big, imposing front cliff face, but that then in front of the mountain, there's sort of this sloping hill, sort of relatively flat, at least compared to the steepness of the mountain itself in the front of it. Okay, so let's go back to the topographical map. Now, what's happening here is what you're seeing is a whole bunch of level curves of contours. So for example, a contour like this one that's got 2120 meters on it just means that that's about a little over 2,000 meters tall when you're walking along that contour. By the way, you'll notice that there's this initial region where the contours are all really close together. What that means is that with small horizontal changes, you get big increases in height. That was those big cliffs we just saw. And then there's this other sort of larger portion where the contours are further apart. So that means over a larger horizontal distance, are you going to be able to get to an increase in height to go from one contour to the next? Those are sort of those flatter, more rolling hills we saw in front of the mountain. Now, if you actually want to climb the mountain, well, you don't really want to go up the cliff face unless you're more skilled than I am. When I do it, I actually just go up the backside here, sort of up this little ridge. And this ridge is nice because as you go along it, it's not as steep as going up sort of the big cliff face. So I sort of go around the back from the picture I took and had shown you earlier. Okay, so let's get back to the calculus then. If I want to look at some point, so I've just put a random dot on, I want to imagine you're standing there. I'm on one of those contours. I'm on one of those level curves. Then the way we can interpret this is that the tangent vector is pointing along that curve, and this is the dr dt, and then the normal vector is going to point normal to that, and it's going to point exactly up the cliff face. Okay, and then the same point when we actually look at the image of it, well, I put my point on the mountain, and then if I look at the tangential vector, this would just be going along at the same height, just moving along the mountain, but not going up and not going down. And then if you go in the direction of the gradient vector, you would rise as fast as possible. You'd be going directly up these cliffs. Now I should just clarify that the gradient vector lives down in the xy plane. It's truly a vector that's pointing into the mountain from our perspective, not going up in the z component, but I just drew it this way, just try to give you a little bit of a perspective on it. But truly it should be thought of as going into the mountain, living in the xy plane. Now, when you're actually climbing mountains and you're trying to use a topographical map to orient yourself and to plan a route through the mountains, the analysis of these contours are actually really, really important. For example, if you're doing any sort of winter sport involving skiing or snowshoes where you don't want to do big rises and then drops in elevation as much as you can avoid it, because that's an enormous amount of work, in any plot that you want to do, often you want to try to contour or to stay as close to a contour as possible so that you can sort of go horizontally without the much larger amount of work of trying to climb the mountain and then go back down again, climb it back down again. You sort of want to contour around. And so this is a very common thing when doing route climbing, try to sort of figure out the minimal pathway to reduce the amount of uphill that you actually have to do as you're navigating.